Our planet Earth is a restless giant, a living, breathing entity constantly reshaping itself through powerful forces hidden beneath its surface. Volcanoes erupt with fiery fury, continents drift apart and collide, and earthquakes send tremors across the land and sea. But these dramatic events are all intertwined, connected by a fascinating process called seafloor spreading, a cornerstone of the theory of plate tectonics. Welcome to the scientific adventures of Beardman. In this video, we'll embark on a journey to the depths of the ocean, where hidden mountain ranges hold the key to understanding how Earth's crust is born, ages, and ultimately recycled. Deep within the Earth's heart lies a source of immense heat, the core. Check out this video to see more about the core and the other layers of the Earth. This internal furnace, fueled by the planet's formation billions of years ago and ongoing decay of radioactive elements, is the engine that drives the movement of Earth's tectonic plates. Check out this video to see more about radioactive decay. This churns heat in the mantle, the thick layer of rock beneath the crust, creating vast, slow-moving convection currents. Imagine a pot of thick soup simmering on a stove. The hot soup rises, cools at the surface, and then sinks back down, creating a circular flow. This is similar to what happens in the mantle. These convection currents drag the tectonic plates along with them, like rafts on a slow-moving river. And it's at the mid-ocean ridges, these colossal underwater mountain ranges hidden beneath the waves, where this internal heat engine gives birth to new oceanic crust. These ridges, stretching for thousands of kilometers across the ocean floor, are where Earth's plates are pulled apart, creating space for fresh magma to rise from the depths. Driven by the relentless heat from below, molten rock called magma rises from the mantle at the mid-ocean ridges. This magma, lighter than the surrounding rock, ascends through cracks and fissures, forcing the tectonic plates apart. As the plates separate, the magma oozes into the gap like a fiery molten river, creating new oceanic crust. This magma cools and solidifies in a variety of ways, creating a fascinating tapestry of rock formations. Some of it erupts explosively onto the seafloor as lava encountering the cold seawater, rapidly solidifying into pillow basalts. These rounded formations, resembling giant pillows stacked on the ocean floor, are a testament to the rapid cooling process. But much of the magma rising from the lower mantle never reaches the surface. Instead, it cools more slowly beneath the seafloor, forming gabbro, a coarse-grained igneous rock with large crystals. These different types of rock, formed through different cooling processes, make up the layers of the oceanic crust, a complex and dynamic structure. To study these rocks and unravel the secrets of seafloor spreading, scientists embark on expeditions to the mid-ocean ridges. They use specialized research vessels equipped with advanced technology, like remotely operated vehicles, ROVs, to explore the depths and collect samples. These rock samples, carefully retrieved from the ocean floor, are then brought back to laboratories where scientists use a variety of techniques to analyze their composition, age, and magnetic properties. Now, let's take a look at some of the evidence that seafloor spreading is actually happening. One of the most compelling pieces of evidence for seafloor spreading comes from the age of the oceanic crust. Scientists have discovered a remarkable pattern. The further you get from the mid-ocean ridge, the older the crust becomes. In this map, you can see the red color represents the rock that is forming right now, 0 million years BP, before present. These locations are the mid-ocean ridges where new rock is found. The green and blue color represents rock that is 80 to 180 million years old. And you can see it is located far from the mid-ocean ridges and near the edge of the continents. This supports the idea that new crust is formed at the ridges and gradually moves outward as newer crust is created, like a conveyor belt, constantly generating new material. This pattern of aging crust, symmetrical on either side of the ridge, provides powerful confirmation of the seafloor spreading hypothesis. It points to a picture of a dynamic ocean floor, constantly being renewed and reshaped by the forces of plate tectonics. Another compelling piece of evidence for seafloor spreading comes from the magnetic patterns found in the rock of the ocean floor. Earth's magnetic field, like a giant bar magnet, has flipped its polarity many times throughout its history, with the north becoming south and the south becoming north. These flips are recorded in the iron-rich minerals within the rocks as they solidify. Whew! As new crust forms in the mid-ocean ridge, the iron minerals in the magma align themselves with the Earth's magnetic field, like tiny compass needles, locking in a record of the magnetic polarity at that time. This creates a pattern of symmetrical stripes on either side of the ridge, with the stripes mirroring each other. These magnetic stripes act like a timestamp on the ocean floor, providing a record of seafloor spreading over millions of years. This magnetic record, combined with the increasing age of the oceanic crust with distance from the ridge, provides compelling evidence for the continuous creation of new crust at mid-ocean ridges and its outward movement over time. But how do scientists actually determine the age of these rocks? They use a precise and ingenious technique called radiometric dating. This method relies on the decay of radioactive elements within the rocks, elements like potassium-40, that decay into argon-40 at a predictable rate. Think of it as an hourglass, where the sand falls at a constant and measurable rate. Radioactive elements decay at a known rate, and by measuring the ratio of the parent element to the daughter element it decays into, scientists can calculate the age of the rock with remarkable accuracy. More detail about radiometric dating can be found in this video I'm linking up here. This technique has allowed us to create detailed maps of the age of the ocean floor, revealing a fascinating story of Earth's history. And here's a surprising discovery. The oldest oceanic crust is typically around 200 million years old, a mere blink of the eye compared to the age of the Earth itself. In contrast, some continental rocks are over 4 billion years old. Why the big difference? It has to do with a process called subduction, where oceanic crust is recycled back into the mantle. Seafloor spreading is a key driver of plate tectonics. The grand symphony of Earth's dynamic crust, it explains how continents have drifted across the globe over millions of years, shaping the world we see today. The separation of the Americas from Europe and Africa, the colossal collision that formed the Himalayas, and the ring of fire encircling the Pacific Ocean. These are all testaments to the power of seafloor spreading and the movement of tectonic plates. Seafloor spreading is a continuous process, a ceaseless ballet of creation and destruction that shapes our planet. If you enjoyed this video, please click on the like and subscribe buttons and check out some of these other videos. Thank you for investigating the ocean floor with us, and we'll catch you the next time on the scientific adventures of Beardman.